Hello, here we go. I'm just going to go over why these answers are right versus why they're not. So here we go. So a certain program language uses 4-bit binary sequencing to represent non-negative integers. For example, the binary sequence 010 represents the corresponding decimal 5, and the programming language attempts to add the decimal values 14 and 15 and assign the sum to a variable total. Which of the following best describes the result of this operation? Okay, so we have 4 bits. So if we had, with 4 bits, you can represent 1, 1, 1, 1. Now remember, in these different spots, they mean different things. Base 10 system, everything's by 10. So like this would be 0 through 9. Then we could go tens, hundreds, and thousands. But in binary, it's different. This represents 0 or 1. This represents 2, 4, and 8. So if we have an 8 here, a 4, a 2, and essentially a 1, we could add those values together. 8 plus 4 is 12, plus 2 is 14, plus 1 is 15. So this number right here is 15. We can't represent any number bigger than 15. So what happens is if we want to do the sum of 14 and 15, we're going to end up with 29. We can't show 29 with 4 bits. So we call this an overflow error. Now B is incorrect because we can represent 14 and 15. That's not true. We could represent 14 and 15. We can't represent anything over. It's not a round-off error because this isn't like decimals. We can take care of it. And no, the correct sum of 29 will be assigned to the variable total. No, it won't, because we can't take care of that. So it doesn't work. ASCII is a character encoding scheme. For example, the letter G is represented by the decimal base 10 system 71. The partial list of their characters are shown here. So we have base 56, but this is in hexadecimal. So if hexadecimal is base 16 system, so the first one is 16 to the 0 power, the second one is 16 to the 1 power, and we're showing a 6 here, and we're showing a 5 here. So mathematically, how would we do that? Well, a base 10 system, that would be 6 units, and this would be 5 times 10, because we put a 10 here, and that's what we would have. So this is going to be still 6 units because it's base 1. So we know it's going to end in a 6, so it's got to be something that ends in 6. So it could be 86, it could be 76, it could be even up there 66. So it's got to be one of those numbers, because I know it ends in 6. And then we're going to do, this number is 5 times 16, which, as a math teacher, I should know off the top of my head, but I don't want to be wrong. So I got my trusty rusty calculator, so that's 80. So this is 80. So this represents overall 80 in the decimal value. This represents 6. Add that together, you get 86. So we must be looking at V as our correct answer for that one. So that's the easiest way to break it down is, remember, base 16, we start at 16 to the 0 power, which is just 1, right? Anything to the 0 power is 1. So 6 times 1 is 6 units. And then 16 to the first power is 16. So 16 times 5 is 80 units. So add that together, and it turns into our decimal equivalency that we're used to. We get V. There we go. Bam. Boom. Good. Moving on. That is not what I wanted. All right. So we're doing RGB. We're trying to select the binary triplet for indigo. Here's a fun trick. These are all obviously in decimal. If it ends in a 1, it is an odd number. If it ends in 0, it's an even number. So this is what I always do first. I just look and I say, all right, indigo is odd, even, even. So which one of these are odd, even, even? So obviously the right answer is, so just by cheating, I know it's A or C. It's one of those two. And my only discrepancy is right here. Oh, and here. And so I'm going to look at this number because it's the right number. And that should be 75. Let's see if it is. So remember, this is 2 to the 0 power. So this is the ones category. 2 to the first power, 2. This is 4, 8, 16, 32, 64. So I have 1 at 64. So 64 plus an 8 plus a 2 plus a 1. So what does that equal? 75. And that's what our first number is for indigo, 75. So we know C is the right value. So again, you could always write this out, remembering that this is 2 to the 0 power, to the 1 power, to the second power, to the third power, so on and so forth, and figure it out, which is awesome. Which one's ivory? Notice it's every value. So this is, what is this? How many bits is this? Does it say? I know, I'm just too lazy to count. I think it's 8-bit. 8-bit. So it's going to be 255, because if you go one more up, it would be 256. So it should be 255, 255. And then the last one's really close. It's just not those numbers. So I'm thinking it's the biggest number. Probably 224, 240. I think it's 240. Just count it out, and you should get ivory. This question is basically saying, I'm increasing my bits by 1. What happens? Well, you're basically multiplying it by another 2. So like that'd be like in decimal. If we said, what's the difference between going from 10 digits, 3 spots, 2 spots to 3 spots? Well, that'd be multiplying by 10. So this is multiplying by 2 because it's base 2. All right, video game character can face one of 4 directions: north, south, east, west. Each direction is stored in memory as a sequence of 4 bits. A new version of the game is created in which the character can face one of 8 directions, adding northwest, northeast, southwest, and southeast to the original 4 possibilities. Which of the following statement is true about the 8 directions? Well, 4 bits is enough, because 4 bits, 1, 2, 3, 4. We can represent 1, 2, 4, and 8. So we can represent a total of 15 different things. And there's only 8 directions, so that's plenty. I don't need a bit for each direction. A lot of people will say 8 bits, but that 8 bits can hold 255 things, so that's not right. Yeah. In a certain computer program, 2 positive integers are added together, resulting in an overflow error. Which of the following best explains why the error occurs? Well, it means you probably don't have enough bits. So it says the program can only use a fixed number of bits to represent integers. The computed sum is greater than the maximum represented value. That is correct. Attempt performing operation is considered undecidable. If it's an overflow error, it's not going to be undecidable. The precision won't matter if it's an overflow. Cannot represent integer converted to decimal approximately. No. Overflow does not have rounding. A video streaming website keeps count of the number of times each video has been played since it's first added to the site. The count is updated each time a video is played, and it's displayed next to each. At one time, the count for the most popular video was about 2 million. Sometime later, the same video displayed a 7-digit negative number as its count, while the counts for the other videos displayed correctly. Which of the following is likely? The count became larger than the maximum value by the data type used to store, and it had an overflow error, basically. So when everything gets too big for something, it's usually an overflow error. Rounding error won't happen because a view is a full view. The software used to update the count failed when too many videos were played. No, that won't work. The software used to update the count contained a sampling error. No, no sampling error. We got too big. Too big. Rounding overflow error. The player's controls in a particular video game are represented by numbers. The computers and their corresponding binary rate are showed. So these are all the different maneuvers we have. What is represented by the decimal value of 15? So that's all that's 111. We did that one earlier. So it's actually 01111, which is down. We're going down. All right, cool. Let's close this. I am now going to go to part 2. All right, here we go. Which of the following can be represented by a sequence of bits? An integer, an alphabetical number, and I'm assuming everything, because everything a computer does is in bits. That was dumb. Which of the following is a true statement about the data that can be represented? characters, colors, audio. Yes, everything can be shown in binary because you can break binary down into infinite number of things, and the numbers can be translated to something else. The numerical value for the controls can be represented in decimal. What is the decimal value for jump control? So we just have to go to jump, and again, I just do this and say, all right, well, this is the 1 position, 2, 4, 8, 16. So you just add 8 and 16 together, and that's 24. Was that the right answer? Yeah. Consider 4-bit binary numbers, which the following decimal value is not equal to one of these. So again, we would say that's 15. That would be 2 and 4. That's 6. And that is 1 and 2. That's 3. So 9. And again, if you don't know binary, there's so many questions. It's worthwhile to figure that out easily. Which of the following best explains how an analog audio signal is typically represented by a computer? So analog audio would be like if you walked in the room and started playing a guitar and you're hearing that. It's not digital, it's analog. So an analog audio signal is measured at regular intervals. Each measurement is stored as a sample, which is represented at the lowest level as a sequence of bits. It's exactly how it works. It's regular intervaling. We call it sampling. Let's just read the other ones real quick. An analog audio signal is measured as input parameters to a program or procedure. The inputs are that. Analog is measured as a sequence of operations. No, we're looking for sampling. It's measured as text. No, that's way too early. Measured as text. That's unnecessary. The position of a runner in a race is a type of analog data. That is true. The runner's position is tracked using sensors. Which of the following best describes how the position of the runner is represented digitally? Again, we're looking for regular intervals. That's a keyword we want. And that's probably in this answer. The position of the runner is sampled at regular intervals to approximate real world position in a sequence of bits. That's exactly what we're going to do. That's how we take information from analog and digitize it if it's a continuous type of data, like a running or music or something like that. Keep doing that. And if you can hear, that's my daughter crying because she doesn't want to go to sleep. Just in case you're wondering, not my newborn son. All right, a binary number is to be transformed by appending 3 zeros to the end of the number. For example, 11101 is transformed to 11101 with 3 zeros, which is the following correctly describes the relationship between the transformed number and the original number. Well, in math, if I took a 2 and then I took a 2 with 3 zeros, what happened? Well, everyone would say we multiplied by 1,000 because that would be 10 to the third power. So what are we doing? If I had a 1 and then I put 1, 0, 0, 0 in binary, we're multiplying by 2 to the third power, which is 8. So that's kind of what we're doing. All right. IPv4 is 32-bit. IPv6 is 128-bit. Which of the following best describes the result of this? Okay. So basically for each additional bit, we're doubling. So we want 2 to the however many extra bits we have. Since 96 is how many more bits we have. Then for each level, we're multiplying by 2. So it's going to be obviously 2 to the 96, not 96 times, because each additional bit is actually 2. So if I went from 32-bit to 33-bit, that'd be times 2, because I only added 1 bit. But I'm adding 96, so it's 2 to the 96 power. Each student that enrolls at a school is given a unique ID. If the ID is assigned to the last student enrolled, was this binary? What binary will be assigned to the next student? These two ones get pushed up, so that becomes a 1, and then 0, 0. So remember, it's kind of like how our numbers work. Once you hit 9, then the next number goes 0, and then the next one pushes up to 1. So we're at 1, 1. That pushes this to 1 and these back to 0. So, hey, we're done with that one. Okay. Whoops, I went off the board somehow. Okay, how do I, no, I want to get out of this. Oh gosh, oh gosh. Maybe if I go to the top, there we go. There it is. All right, last one. Okay. A story uses binary numbers to assign unique sequences. What's the minimum number of bits required? 75 to 100. So 8-bit, most of us will know 8-bit is 255. If you didn't know that, that's okay. If you divide 255 by 2, you get about what? 128? I think it would actually be 127, but about there. Because usually we are used to hearing 256, 128, and you can actually store those values. It just starts at 0. So that would be C, 128. This would be half of that. So you just kind of keep cutting in half to get to your value, because one less bit, divide by 2. One more bit, multiply by 2. Considering the following, which of the following is in least to greatest? Well, again, this is, if we were to do this out, again, we have 1, 2, 4, 8 position. So that's going to be a 8 plus 2 plus a 1, so that's 11. That's 8 plus a 4, which is 12 plus 1, which is 13. So the smallest is 5, and then it's the 1, 0, 1, 1, then 12, and then 1, 0, 1, 0, 1. Just gotta do it's like the flippy do. Okay, whenever you have decimals, look for um, rounding error or floating point is what they'll call it a lot of times too. So overflow, it's not overflowing, the number's not too big, the program intended to execute with operation, no. The program intended to represent a floating point number as an integer. The precision of the result is limited. So we are always limited when we're doing decimals, because we have a difficult time with decimals. So usually we round that. So this is a floating point representation. It doesn't go all the way. A student is recording a song. When the song is finished, she saves a copy. Notice it's the lower quality sound. Which of the following happened? Well, you saved it with less bits. That means less sampling was taking place. So the intervals were longer, not shorter. And so you're going to have, not as good a quality. If it had more, then that'd be good. The song was saved using a lossless compression. That means it didn't lose any, but obviously it did lose some. Some information is lost every time a file is saved from a location on a computer. That's not true. It's just how it's compressed. If you save it on one computer and then you take that file and you save it onto another, it should be the exact same unless you're compressing in some way. A program developed for a web store represents customers' account balances using a formula that approximates real numbers. While testing the program, a software developer discovered that some values appear to be mathematically imprecise, which is the most likely is the cause of imprecision, rounding error. Okay, so that's an instant one, but the question is it B or D? So we can use an unlimited number of bits in the world, but no computer will use unlimited number of bits because it can't store unlimited number of information. So don't ever pick anything usually where something's going to use unlimited, because it's just not feasible. We could theoretically have unlimited number of bits, but practically we can't actually do that. Just like you could theoretically continuously count in decimal forever, but you can't realistically do that. So that's why this one's right. You have a fixed number of bits. All right, a text editing application uses a binary sequence to represent each of the 200 characters. What's the minimum? It's got to be 8. We had the same one before. Remember, this was 126. This is 256. Or sorry, 128. So it's gotta be day. Okay. Office uses an application. So now we have 100 staff members. This is 128. So what's half of 128? That's going to be 50, 64. 64-bit. Not enough. Just enough. Okay. Some programming languages use constants, which are variables that are initialized at the beginning of a program and never change. Okay, so to represent the mathematical pi is 3.14. So which of the following are good use for a constant? Okay, that would be good because pi does go on forever. To represent the current score in a game. So since they're initialized at the beginning of a program and never change, the current score in a game. The problem is the score of a game changes over time, doesn't it? So that would not be good. To represent known values such as the number of days in a week. That would be good. Number of days in a week is always 7, doesn't change. So we're looking, the key here is it never changed. That's why 1 and 3 is the right answer. Current scores can change. So no bueno. So 4-bit to represent non-negative integers, which the following statement describes a possible result when using this program. Again, since 4 bits can only represent 15 at the highest, this is the only one that will have an overflow. It can represent 15, so that would work, and that can work. So it wouldn't be an overflow. Just 2. That'd be the only one. It's the only one that's over 15. I hope when you watch this video, you're like, oh my gosh, this is so dumb. I can't believe I missed these. Which of the following can be represented by a single binary digit? The position of the minute hand. Well, minute hand has 60 options, so no. The remainder when dividing by a whole number of 2. Yes, because the remainder is 1 or 0, so that's only 2 options. The volume on a car, unless you have a really ghetto car where it's either off or on, it doesn't seem like a volume to me. The value of a Boolean is usually a yes or no question, true or false. So anything that has 2 outcomes is a Boolean variable, which works for us. All right, guys, so that is it. I hope that was helpful, and I hope it wasn't too long. Next time.